Okay, I'm gonna, now that you've looked at parity bits and parity words and you understand what that is, I want us to now look at a spectacular use of parity bits, which uses even parity, and it's called the Hamming code by Richard Hamming. Now, all the positions in the Hamming code word that corresponds to powers of 2 are reserved for parity bits. Right, let's say I've got a message. Let's say my message M was given by, let's say I want to transmit the word 1011 using the Hamming code. What I'll do is I'll call this M1, I'll call this M2, I'll call this M3, I'll call this M4. Let's say what we'll then do is we'll then say, oh, I don't know, the pen is misbehaving. M1 is called our first one, M2 is our second one, which is our second bit. This is the message bits. M3 is our other one, this third bit, and then M4, message bit number 4, is the last one. So this is our message. What we then do, we know that these here are going to take up, if we now then say, okay, the positions, we are going to have position 1, 1, 2, 3. So this is the power of 2, this is 2 to the power of 0, this is 2 to the power of 1. So all those positions in the Hamming code word that correspond to what? All positions that correspond, there is my English, that correspond to powers to what? To powers of 2 are reserved for parity bits. So this here therefore is our parity bit, our first parity bit. That there is our second parity bit. This is not a power of 2, so this is where our what? Our M1 is going to come in. So our M1 is going to come in there. Then this is 4, but remember that this is a power of 2, 2 to the power of 2, so this will be our third parity bit, P3. All right, we said we're going to name them P's. All right, now, so our next position in the number is 5. That's not a power of 2, so that will be our second message bit. Now 6 is not a power of 2, that will be a third parity, what called message bit. Then 7 is also not a power of 2, that will be what? Our fourth. So our number, once our entire number is taken care of, we don't need to go further, so we'll cut it at that point there. Then how do we then determine, what do you call this, how do we then determine our what? Our parity bits P1, P2, and P3. Now if you look at because I'm gonna call this correction bits. Let's put our correction bits. I only need 3. 1 to correspond to C4, 1 will correspond to C2. I'm using here 4, 2, and 1. Why? I only have those powers 4, 2, and 1. So our correction there is, our detection and correction there is going to use C bits. So that will be C2 and that will be C1. Now if we look at our position, I'm going to put our position down here. Our position 0, we don't have position 0, let's keep that. Our position 1, a number cannot be have a position. I'm going to start writing on the first position. Position 2, position 3, position 4, position 5, position 6, position 7, because we have 7 positions. We would have gone further if we had more positions. So I'm going to deal with a specific example. So now our count, now if you look at the count using the what? The 4 to 1, this will be 1. Okay, that will be 2. That will be 2 and 1. That will be 4 with nothing. 5 will be 4 with 1. 6 will be 4 with 2. And 7 will be 4, 2, and the 1. Maybe I should have said this is also our parity bit. This is going to work both for parity, for working out the parity bits, and it's also going to work for correction. Okay, so for parity, we're going to have, this is our P3, our P2, our P1, our first parity bit. So what happens is that on the positions, the parity bit 1 is going to check everywhere where the count has a 1. Like you know, P1 is going to check count 1 because there's a 1 there, count 3 because there's a 1 there. So you can see it's all the odd counts. You can rest assured the next one is going to be a 9. Following one would have been a what? An 11. So P1 checks all the odd counts. So P1 checks. Let me rather save space. I may need more space. I want people to be able to refer to this session here without going in another page. So P1 is reserved to check odd counts, and the odd counts are count 1, count 3, count 5, and count 7. In this case would have gone on if what. So now what does it do? It then says we are using even parity. So all the message, on the message that we're going to transmit, all the bits that are going to fall in these positions here are going to be what? Are going to have an even count of ones. Now, what do we mean? We have 1, which is P1 itself on the message. That will be P1. We have got, I'm adding, I want to have an even sum. We've got 3, which is the first bit of the message, M1. We've got 5. 5 is the second bit of the message. And we've got 7. 7 is M4. So all these here must give us, maybe I moved a little bit too much. I'm running out of space. Let me try and get some space. So all these bits here are going to what? I'm going to have that struggle that I had before. Okay, I'm just going to have to squeeze it. We are struggling here. This is going to be an even count. Oh, okay, let's use another trick. Let's just drag this a little bit. This is going to have 2. That sum is going to have to be even. What are we trying to do here? We're trying to say it's going to check those specific what? Those specific positions, and it's going to look out for what? An even number of what? Of ones. So if we look now, you look at your P1, we don't know what that is. We're trying to determine what it is. P1. Oh, I already have a pen. Therefore, P1 plus message 1, we said it's a 1, plus the second message, you said there it's a what? It's a 0, plus the what? The message bit number 4, we said it's a what? It's a 1. This is supposed to give us an what? An even count. To achieve that, it's only possible if our P1 is a 0 itself. Why? We already have 1 plus 1, which is 2. If P1 becomes another 1, that will be 3, which won't be even. So it has to be a 0. So what we are happy. So we know now that our P1 here is a what? Is a 0. Okay. Now what about P2? P2, the count everywhere where the what, where your position has a what, carries a weight of 2. You are going to, let's look at 2. 2 is 2. 3 is 2 and 1. 6 is 2 and what? And 4. 7 is 2, 1 and what? I'm worried about the 2s. Everywhere where we are seeing a 1 under what? Under P2, or the position that carries that in binary would carry what? A weight of 2. All those positions are going to be what? Are going to be checked by P2. So P2 checks the position 1 does not have a 2. Position 2 has a 2. Position 3 has a 2 because it's 2 and 1. Position 4 does not have a 2, it's only 4. Position 5 is 4 and 1, not 2. Position 6 is 4 and 2. Position 7 is what? It's 4, 2 and 1, so there's a 2. If we were to go on, if the number was longer, position 8 wouldn't have had a what? Wouldn't have had a 2. 9 wouldn't have had a 2. 10 is 8 and 2, so we would have had 10 next, but our number doesn't go that far. So 11 is 8, 2 and 1, so would have, P2 would have checked 11 if the number was that long, but we only go as far as what? As far as 7 with our current number. So what it means therefore is that these positions here would have to give you what? An even number of what? An even number of ones as well. So what does it mean? P2 is 2, which is obviously therefore our first what? Our first P2 is 2 itself, so it's our first one. Then if we add that to 3, but 3 here is what? Is the first bit of the message, M1 plus. If we now look at the next one, there is 6. 6 is what? The third bit of the message, M3 plus. 7, you already know 7, we've done it in the previous one, is what? M4. What am I doing? I want it to be nice and neat. We can't request neatness from our students and fail to be neat ourselves. Okay, that will be that will be Pycotry. That will be Pycotry of academic Pycotry. Now, if we then look at this now, we then have to say, therefore, it means that P2, the first P1, the M1, the first bit of the message is a 1. This, we are looking at the third bit of a message. The third bit of a message is what? Is M3 is a 1. Then we know the last one, M4 was a 1 as well. So these ones here would have to give us a not an even sum. Why? Hamming code uses even parity. So what are we seeing here? We are seeing that our parity bits are checking specific positions, and all they do is go back to even parity. Now, for this to be possible, P3 can only be a what? P2, sorry. P2 can only be a what? Another 1. Why? 1 plus 1 plus 1 plus 1 will be a 4. 4 is even. If P2 can only be 1 or 0, if P2, this is still binary. It's a binary code. So if this was a 0, our answer would be 3, and that's not even. So for it to be even, we need to P2 to be what? To be a 1. Now, obviously, now it will be easier, perhaps, to work out P3. P3 checks. Remember, P3 corresponds to what? To the weight of 4. So every position in the what? Every position that what? That if it was converted to binary, it would have a weight of 4. It would have a weight of 4. Every position that has a weight of 4 in it would then have what? Would then be checked by P3. So if we look here, the first position, 1 doesn't have a 4, 2 doesn't have a 4, 3 doesn't have a 4, 4 obviously has a 4, so that will be the first one. But then now, 5 is a 4 and a 1, so everything with a 1 on the 4 will have to be checked. 5 is 4 and 1, 4 is there. 6 is 4 and 2, 4 is there. 7 is what? 4, 2 and 1, 4 is there. 8 doesn't have a 4. If the number was longer, 8 would have been checked. 9 is 8 and 1, doesn't have a 4. 10 doesn't have a 4. 11 doesn't have a 4. Now, 12 on the other hand, if we're a 12-bit number, then position 12 would have been checked. So I'm just saying, just be careful that these are not the only positions. If the number gets longer, we still have to look out as long as the position has a what? Has a weight of 4. Now, if we look, then this would mean that we would have to have an even sum. 4 is the third parity bit itself. So P3 plus position 5 is M2. M2 is a 0. And then plus position 6. Position 6 is M3. M3 is a 1. Plus position 7. Position 7 is a M4. M4 is a 1. And what does it tell us? It tells us that this must be not an even sum. Because, why again? The Hamming code uses what? Even parity. Now, and then now, if we look at this now, this would mean, therefore, I should have said therefore P3 would have to be, for this sum is already 2, for this sum to stay even, it would have to stay 2, P3 would have to be a what? A 0. Why? If it was a 1, then the sum becomes 3, 3 is not even. So, what does it mean? We didn't come and say what our P2 was. It's a 1. Our M1, we already knew this was our message that we were trying to protect. It's a 1. Our next one there, P3, we just worked it out to a 0. Our position 5 is actually a what? An M2, which is another 0. Position what? 6 is M3, which is a 1. and position 7 is a 1. So this is the code word. This is the Hamming code word that would what? That will have to transmit. This is, I'll just say HC for the Hamming code word. So when you transmit, you're going to transmit 0110011 as our Hamming code word. So what do you note here? You note that if we check P1 checks, look at, we are in the previous scenario where we're using only parity bit. What are we doing? A stream of what call this, even a byte of what call this, a byte of digits could have been protected by what? By only 1 bit, and you saw how dangerous that was. But look at this now. We are having 3 parity bits protecting 4 bits of data. Okay, and if we had a longer number, would have had more bits to check that. Now, look at this. P1 checks 1, 3, 5, and 7. P2 comes and double checks 3 and 7 again. So you can see that data is not protected only by 1 bit. If you come here, then again you can see that 6 and 7 is protected again here. So you find that you find that your protection is, you've got more protection. P1 protects position 1, is the only one that protects position 1. But if you look at P2, position 2 is the only one that protects only position 2. But if you look at position 3 now, it's protected by 1, 2 of them. Maybe we could have had more. Okay, if we had the count 10, probably would have gone to P4 protecting that, depending on how long the number is. So obviously the number of protections that we need depend on the length of the number. So it's, what I'm trying to point out here is that you've got P3 and P1 checking out for what? For 5. So digit 5 is not only protected by 1 bit. So there's no 1 bit except for 1 and 2 perhaps that are only protected by what? By single parity bits. The rest have got double or more protection. Now, if we then look at let's suppose now in transmission, we transmit this word, transmit. That's our what? Transmission. Let's say we transmit this word, okay? But the receiver now receives 0, 1, 1, 0. Somewhere that went wrong, 1 and 1, 1. This is not what we transmitted. We transmitted 011, 0011. But now it was 011, it's not 00 anymore. This has gone corrupt. How will this code then detect and what? And correct this? This is where the correction bits come in. Okay. We come and say for C1, for correction bit C1, okay, this will be what? We'll look at what P1, C1 comes with P1. P1 checked for us. We look at what P1 actually checked. It checked positions, all the odd positions, 1, 3, 6. Oh, sorry, I'm saying 6. I meant to say odd, which is 5 and 7. Now, if you look at those, the sum was supposed to be even. Check that these are actually even. So what P1 checked. Okay, let's see if you are happy. 1, 1. So where is our 1? This is position 1, 2, 3, 4, 5, 6, 7. Now 1 is a 0 plus our 3 is a 1 plus our 5 is a 1 plus our 7 is a 1. Is this even? Our answer is not even. When it's not even, this is uneven. It's supposed to be even, so this is uneven. We say uneven by making a C1, sorry, declaring C1 a 1. Correction bit C1 says 1. When it says uneven, it says 1. When it says happy, it's trying to make, it's trying to say go back to even. You are short of a 1. All right. So then you go and say P2. Now we're checking out for correction bit number 2. P2 checked. Every count with a 3. Every position with a 2. Every position with a 2. So 2, 2 and 1. 2 and 4. 2, 4 and what? And 1. And this was supposed to be even. As long as the position at a 2, it checked those. Let's see if that's still true from our message. Position 2 is a 1. Position 3 is a 1. Position 6 is a 1. Position 7 is a 1. And it says, yes, you are even, and therefore declares even. And therefore what we do, we declare C2 does not need correction. Is a what? C2 is a 0. Okay, now the last one, C3, comes from P4. Okay, correction bit 4, sorry. C4 comes from P3. I'm having it twisted. Position 3. Okay, C4 is because P3 checked. It's checking. It's checking and correction. Eh? So checking, it checked. P3 checked. Everything with a 4, that's a 4. 4 and 1, 5. 4 and 2, 6. And 4, 2 and 1, which is 7. And it says you should be even. Checked if this was even. Now if we look, position 4 in our received number is a 0. Position 5 in our received number is a 1. 6 is also a 1, and 7 is a 1 as well. Now it says no, this is not even, and therefore C4 is declared a 1. All we do is come and say, but this is our error. So if we are checking here, our error is given by C4, which is a 1, C2, which is a 0, and C1, which is a what? A 1. And this is the count 5. What does it tell you? It tells you this is the count. If you take it from this is the most significant. If you take it up, you can see that this is what? This is 101, which is the same as 5. In base 2, which is the same as 5. So therefore, what does it tell you? It tells you bit number 5 is faulty. So it means, since it's a correcting bit, it won't even tell you, it will just change. So you say, okay, correct information was, let me just try and see if I can get a space here. So the correct word here was, where do I put it? It will correct the information, correct to 0, 1, 0, but that 1 is changed automatically to what? To a 0, 1, which is exactly what you transmitted. So this is the correct 2, 0, 0, yeah, this is our correct information. So you can see how we reserve. First of all, we are using even parity. Then what do? We all positions that are powers of 2 are reserved for the parity bits. The other message bits are fill up the rest. Okay, and then you see how we've done this. All you do is your parity bits, just know which one checks what, and then at the end of the day, the correction bits are just a what? Are just a layout. They represent the number of the number in binary, the position number in binary of the bit that has gone over. Okay. So there's more to the Hamming code. This is just the basics. There's more to the Hamming code. I would like to mention, however, that there is this that I must mention. So if I gave you a number, I said 1011, and these are what? These are 4 bits. So are we always going to lay it out first before we know how many parity bits we need? We are going to say, we can't. Engineers can't be that dumb. They can't be that stupid. So engineers always come up with what? With ways of figuring it out without even having to. I can even give you a quick question and say, how do you determine the number of what? How do you now determine the number of parity bits that are going to be required? So the formula we have is 2 to the power of p is equal to, remember we've got the parity bits themselves, the number of parity bits, plus the number of message bits plus 1. Okay. Oh, it's not equal to, rather it is equal to or greater than. Okay, it is equal to or greater than. Greater than or equal to. Alright. Alright. So let's see. We had 4 bits there. We had what? We had 3 parity bits from 4 bits. Let's see if this is true. Right. If you have 4 message bits, like we did have, and then plus 1, that gives us what? 5. These together gives us 5. Alright. So what does it say? It says that 2 to the power of p, if p was 1, let's say p was 1, would have 2 to the power of 1, which is 2. It's already less than 5. If p was 2, that would make this quantity here 4, and 4 obviously is less than 5. Let's make p what? 3 now. If p is 3, that would then be 3 plus 5. That's 8. And 2 to the power of 3 is equal to 8. Therefore, it satisfies the equation, and therefore that's how we know, would have known that what would need 3 parity bits. Let's suppose our number was 1 0 0 1 0 1. Now, how many parity bits do we have? How many bits do we have? 1 2 3 4 5 6. We have 6 message bits here. Message bits for the word. All right, message bits. So what does it mean? It means 2 to the power of the number of parity bits we require has to be greater than or equal to that p plus the number of message bits, which we know is what? Is 5 plus 1. Now if you look at this here, this is already 5 bits or 6 bits. 1 2 3 4 5 6 bits. 6 plus 1, which is a total of 7. Okay, so we need this to be greater than, we need 2 to the power of p to be greater than what? P plus 7. So obviously it's not 1, obviously it's not 2. We tried 3, we saw how it works for what? It was, let's put 3, this will be 10 here. 10 is greater than 8, so that won't work. So let's try 4. If we have 4 now, 2 to the power of 4, 2 to the power of 4 is obviously 16, ne? And 16 is obviously greater than 4 plus 7, which is 11. And this is 11. So obviously 16 is greater than 11. So what do we know? We know, therefore, we need P for parity what? For parity bits. Okay, so let's take our numbers. What do we do? We know our positions are, so 4 plus 7. Ne? So what do we do? Position 1, 2, 3, 4, 5, 6, 7, 8, 9. Maybe let me close this part so that I can have I can move this. Let's say we go then and say 10 and 11. This is P1, this is P2, this is P3, this is P4, and then that is message 1, message 2, message 3, message 4, message 5, message 6. Okay, so we have 6 bits. Yeah, we had 6 bits plus what? The 4 bits. What do we have? We have got what? 10, not 11, 10. All right. So now, why do we have the 1? The 1 is because in our checking, it's possible to have our count being 0. So our counting, when we are doing the C's, I did C, C4, C2, C1, but the counting doesn't start. When you did our counting, we started with 1, 2, 3. Our counting doesn't start there. Our counting starts at 0. Now, what is this 0? When our correction bit is 0, 0, 0, it means that our what? Our messaging is correct. It means that there is no error in the word. Why? because position 000 does not exist in the what, in the number. We remember we started our first one with what, with 1. So 000 means the error is actually not there, because the error is in position 0 and you don't have position 0, so it simply means that the error is not there. But for our correction bits, the count has to include that possibility that there's no error, which is why we have this 1 here. Okay, our bits plus the 1, because our bits are going to count all the way up to what, up to 10 in this case. So our parity bits are going to be able to check all these positions, but so that's why we're saying the parity, the positions for what, for the message, and the position for the parity. But we also have to remember there's a possibility that there's no error, which is why we say we must consider that there's what, we must think about the extra position. Okay, so in this case here, if we try just for the fun of it, I think we understand. But let's do another example. Let's complete this example so that we know what we are doing. We know P1 checks all the odd positions with a 1. So that's position. There's a 1 in 1. There's a 1 in 3, 2 and 1. There's a 1 in 5, 4 and 1. There's a 1 in 7, 4, 2, 1. There's a 1 in 9. And all these must be even. Okay, so if that's the case, what do we have? The 1, P1. This is P1. This here is position 3. If we look at our number here, if we put position 3 is M1, M1 is the first part of the message, which is 1. Position 5 is M2, M2 is 0. Position 7 is M4, 1, 2, 3, 4, and the message bit is a 1. And then position 9 is M5, 1, 2, 3, 4, 5 is a 0. And if you see here, for this to be an even number of ones, implies that, let me rather say, it implies that P1 would be equal to a 0, because I already have 2 1s here, so I can't make it a third one. That would not be even. Now P2 checks all the positions with the what? With a 2. This is the 2 itself. 3 is 2 and 1. 4 has no 2. 5 has no 2. 6 has a 2. 4 and 2. 7 is 4, 2, 1. 7. Then 8 has no 2. 9 has no 10. But 10 is 8 and 2. 2 skip 2, 4 and 5. 2 skip 8 and 9. Well, that will then be what? That will have to be even. Pen is going on strike, or whether the pen is tired or what. So this is P2. We know that's P2. Position 3. That's position 3 is M1, which is a 1. Position 6. Position 6 is M3. 1, 2, 3, 0. And then position 7. Position 7 is M4. M4, 1. And then position 10 is M6. M6 is a 1. That would imply, for this to stay even, that would imply P2 has to be a 1, because there's 3 1s already. Let's make them 4 with P2. P3 checks. This will be 2, 0, 2, 1, 2, 2. This is a 4. All the counts with the 4. That's 4. That's 4 and 1, 5. 4 and 2, 4, 2, 1. And then is there any other one? 8 does not have a 4. 8, 9 does not have a 4. 10 does not have a 4. So we are done. And these will have to be even. What does it mean? Do you know this is P3? Position 5 is M2. M2 is a 0. Position 6 is M3 is 0. Position 7 is M4 is 1. Okay, so if you look at that, 4 5 6 7 4 P3 5 6 7 M2 M3 M4 M2 M3 M4. So there's only 1. What must P3 do? Make sure there's an even number of what? Of ones. There's only 1, make it even. Now if you go and check the last one, then we'll say, okay, now let me just move this whole lot. I moved it too deep last time. Let me just move this whole lot and say we need to do the last one, P4. P4 checks positions. These are positions. All right, that one there is, this is 2 to the power of 3. P4 is 2 to the power of 3. Remember, that is 0, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. This is 2 to the power of 3. 2 to the power of 3 is 8, so it's the position 8. 9 because it's 8 and 1. 10 is an 8. 8, 9, and 10. Oh, what am I doing? 10. So that you would have an even count of ones. We're using even parity. So that is obviously P4 itself, with position 9 is M5, position 10 is M6, 5 and 6, 1, 2, 3, 4, 5 and 6 is 0 and 1, 0, 1. Is this even? It has to be even. So for that to be even, P4 has to be what? P4 has to be another 1, because there's only 1 to make it even. There will be 2 1s if you make 2 4. If you make P4 a 1. So what does it mean? It means that your Hamming code word will therefore be P1 has been worked out to a 0, P2 has been worked out to a 1. The number, this is the number, the first digit is a 1. P3 has been worked out to a 1. And then 5 is the second bit. 5 6 7 are bits. 5 6 7 0 0 1 0 0 1. P3, no, P4, we've done P3. P4 is a 1. And last 2 bits, 9 and 10 is 0 1. And that's the word we would actually what? Transmit. This is our Hamming code word for that 6-bit number. I don't know, I think it's been a little bit long, but I hope it was helpful. I hope people understand, first of all, how do we do the fault. Let me just work on this same scene. Let's suppose that one went renegade and it became a 1, right?